Now, CPU. So what we're going to do is we're going to talk about the CPU. We're going to understand the function of it. And then also what we're going to then do is we are then going to explain the characteristics of the CPU basically, and the keywords I'm going to go through is going to be clock speed, cache size, and number of cores. Okay. So just a little video just to play. So just listen in.
In this video, we will look at what the central processing unit in a computer is and what it does. The central processing unit, or CPU, is often referred to as the brains of the computer. Whilst this is a little misleading, as it doesn't think, it is responsible for all the processing the computer does. Without it, computers would not be able to do anything with the data they store. First, let's take a look at what the CPU looks like. Here is a motherboard with a CPU on it. You can't see the CPU at the moment as it is under the big piece of metal called the heatsink. As the CPU carries out millions of calculations per second, it gets very hot. We need to get the heat away from the processor before it damages it. To do this, we use a heatsink, which draws it out while a fan on top blows air onto it to move the heat away. A fan on the case then blows the hot air out of the computer. This is one of the reasons you may notice that computer rooms without air conditioning can quickly get warm. All the computers in there are blowing out hot air. You will notice the Raspberry Pi doesn't have a heatsink. This is because at its normal speed it doesn't generate enough heat to need one. Generally, the faster the processor is running, the more heat it will produce. The CPU sits under the heatsink. Don't be tempted to take the heatsink off at home. When a heatsink is first put on, a special paste is put on to ensure there is a connection between your CPU and the heatsink to allow the heat to be transferred. Removing and replacing the heatsink without fresh paste will reduce the efficiency of the heatsink. Here is the CPU itself. Inside there are millions of electrical switches called transistors. The most modern CPUs can contain over 1 billion. These transistors are used to build circuitry inside, including logic gates, which are covered elsewhere in this course. Within the CPU, two of the most important parts are the control unit and arithmetic logic unit. The control unit coordinates parts of the processor when an instruction is received. The arithmetic logic unit, or ALU, performs calculations and comparisons. The CPU does its processing by repeatedly carrying out 3 steps. These are fetch, decode, execute. Let's take a look at the fetch, decode, execute cycle. All the instructions and data for the CPU are stored in memory as binary. In the fetch step, the instructions retrieve from the memory to the CPU. The CPU uses something called the program counter to keep track of where it can find the instruction it needs. Once the instruction is loaded into the CPU, it needs to work out what the instruction means. It does this in the decode step. Finally, the computer has to carry out the instruction during the execute step. This could be a number of things, including loading data from memory, storing data from memory, or performing a calculation. The processor will carry out this cycle over and over millions of times per second. In this video, we have looked at what the CPU is and how it works.
Okay, so like it says there, so the CPU is the most important part of any computer system, and every computer system has got a CPU. Okay, it performs all the calculations and fetches, decodes, and executes program instructions. So in other words, when I go through all of the keywords, it'll all make sense. Okay, so there's 2 main parts to the CPU. The first one is called the ALU, and this is called the arithmetic logic unit. And what this will do is this carries out all the calculations basically. So if there's any numerical, if there's any binary that needs to be sorted out, that is where it will all get that's where it'll all get sort of done. Okay. The next one is the control unit. Now the control unit is responsible for retrieving data, okay, and instructions from correct locations in memory. Now the memory is basically, I'll go through memory in a lot more details. It's part of the von Neumann architecture, but just for now, All you need to know is that it's memory and it's executing those instructions. So this is what the control unit does. So if you imagine, if you break that keyword down into control unit, it will control the flow of information throughout the CPU. It might also ask for for help off other pieces of hardware, such as the ALU, if there needs to be any sort of calculations and all that kind of stuff. So what the CPU does, okay, so the first one is it will fetch, which is there. And because it'll then fetch, we are then looking for a decode part. Let me just put this up just so I know I'm not on mute. Good. Okay. It'll fetch it from the memory. So whatever the instruction is that's needed, it'll then go and fetch it. The decode part is basically the instruction to find out what processing to do. Okay, so in other words, it'll understand what it needs to do. And then the execution part is the instruction. So in other words, it'll actually do the instruction that's needed. Okay. Now, when we move on even further, we'll now look at factors now that affect the CPU. So things that might affect the cycle from either going faster or obviously going slower. Now, clock speed. So what clock speed is basically is how fast the CPU can complete that cycle. Okay. Now, basically the clock speed is measured in hertz, megahertz or gigahertz. And what actually happens is the CPU will complete the cycle over and over again. But if you've got a lot of clock speed, in other words, if you've got, say, 5 gigahertz, you can do 5 billion operations per second. Compared to a computer that might have, say 10 megahertz, for instance, that's not a lot, basically. Okay. So again, this is the amount of information that can be processed at the same time. All right. Now, the number of cores. So the number of cores can have a massive impact in terms of the speed of the actual computer itself. So you only need one CPU, but inside of that CPU, you basically have like little mini CPUs, and these are called cores. Now, each core is classed basically as a CPU, like I said just then. Now, if you have got multiple cores in your computer, that means you can process information quicker at the same time. So, for instance, if you've got a dual core processor, that basically means you've got 2 processors, 2 CPUs, which means you can do double the amount of information. Compared to if you've got maybe, say, a quad core processor, which basically means you've got 4 CPUs, which means you can do instructions at the same, you can decode instructions at the same time 4 times over, basically. Which basically means if one computer's got 1 CPU and the other one's got 4, you can do 4 times the amount of instructions, basically. Okay. Another one is CPU temperature. So obviously this comes down to how it will affect the performance. Now, obviously, if you are leaving your computer on all the time, you're not really looking after it, the CPU can get really, really hot. Now, basically, it needs its own cooling system, and this is called a heat sink. And it's actually based on the motherboard and actually sits directly over the top of the CPU. So obviously, if CPU does get hot, like really hot, then it'll actually start to slow down because it's not effective. Now, because it isn't effective, that basically could actually cause damage to the CPU, and in turn, over time, will actually start to lose its speed. Okay. And the last keyword I'm going to go through is going to be cache. It's not catchy, it's called cache. And this, where cache basically means, what happens is the process will go from the fetch part, and then it'll look in cache first to see if it has got any instructions in there that I need. If it's not, then it'll go to RAM, and then RAM then will go to like the storage device and all that kind of stuff, and then it'll then go back to CPU. Okay. Now, cache, all it does is it will store the most recent instructions used by that user. So for instance, if you close down a web browser and then reopen it up dead quick, what will actually happen is it'll actually open up nearly instantly, because it knows where to go for them instructions, because it's already been through the full process once. It basically shortens down the process and just takes a bit of pressure off like RAM and stuff, to make sure that if we are trying to use a computer correctly, then obviously what we can then do is we can then use cache to pull out them most recent instructions that have been used. Okay. And then here's a little diagram. So apologies about the thing. So this does say CPU here. Then this part says it requests data. Now what will actually happen is it will request the data. It will then check to see if the data is in cache. If it isn't, then it'll go to RAM, okay, which is random access memory. Once it's gone to RAM, the data is then copied from RAM to cache. So what will then happen is if we want to use this instruction again in the very near future, it is there for us. And then the data is then obviously sent to the CPU, so then it can be processed. Okay. So that is basically the whole process of a CPU. Now, I have skipped over some of the bits inside of there, but you kind of get the main gist of it. Okay, so what I'd like you now to do is either watch this back or whatever. I'd like you to make a SPI diagram on everything that I've said, everything that I've gone through, and all the little notes in the booklet. When that's done, I'd like you then to answer the questions. Now, each stage should take roughly about an hour each one. So you've got a load of information, make a mind map on it, and then you've got your questions. Them questions are exam questions, so make sure that you try and answer them as best you possibly can.